Hi, I'm Chris.
I'm Joey.
I'm Jovany.
And I'm Josh, and we're Team 5.
The purpose of our project was to model a real-world recycling system by creating a collection and sorting system. Our implementation involved a 3 degree of freedom robotic arm to sort the blocks, a 3-wheeled rover to collect the blocks, and sensors to detect the block attributes. And now here's a video of our live demonstration.
这可怕吗？同学不用怕，看他愿不愿意做。他如果愿意过来，我们就愿意发；他不愿意过来，我们就没话说了。
Josh, actually, could you stop holding that? And it hits the front of the board, remember? So could you just stand there? It's okay. Just let that fall. You don't need any more. Josh, could you breathe it? Did it say edge detected?
Yep, edge detected.
Okay, turn it off, please. Alright, that was good. That was a good preliminary.
Our project constraints included a $400 overall budget. A use of 3-wheeled rover 2.5 was mandatory. Each team member had to use a TI ECE4534 SF microcontroller board, 3 degree of freedom robotic arm that cost less than $100, a Raspberry Pi as a server for communication between all of the boards using MQTT, and having a set boundary for the playing field. Our playing field was a 2.5 by 5 foot elevated platform made from a recycled table. The objective was to have the 3-wheeled rover 2.5 collect all the block units scattered randomly around the playing field and drop it off at the funnel location. This funnel location was marked by a purple flag. The funnel organized the blocks into a centralized area below the elevated platform. From here, a small conveyor belt system fed the blocks to an area within the robotic arm's reach. The statically placed pixie cam right by the arm detected the block color and distance away. The arm used this data to then determine which bin the block belonged in. For communication between the boards, we used MQTT, which is a lightweight publish and subscribe network protocol designed for message transport between devices. We chose the PixieCam 2 as our sensor for navigation on the rover because it was a lightweight and cost-effective solution for detecting block attributes. This includes color, bounding box, and pixel location from within the frame, and number of blocks within the frame. We chose to implement the sensor over I2C bus because it is faster than UART without the additional overhead SPI requires. I2C worked fast enough for our implementation of the PixieCam. We chose the sharp infrared sensor provided because it was free to us to use. It also was good enough to detect edge boundaries of the platform. We used an onboard ADC provided with the ECE4534 microcontroller board to convert analog to digital signals. We then developed a conversion function to convert these digital voltage signals to accurate distance readings in millimeters. We went with a multi-threaded design as a requirement of the class, but also so that each sensor readings did not block each other. Timer callback functions controlled time intervals at which each sensor was pulled. Read tasks then fetched and inserted sensor data into raw data queues. I had 2 more tasks, reading from each raw data queue and converting the data accordingly to sensible data for the rover. This packaged data was then sent to the server, the Raspberry Pi, via MQTT. The infrared sensor was very reliable with a plus or minus 2 millimeter accuracy. This was more than enough accuracy to detect the platform edge all of the time. The PixieCam 2 was 100% accurate in detecting where the block was in the camera frame. The only area of unreliability was in the color detection. Sometimes the camera detected larger objects of similar color in the background. To overcome this, we did our best to remove all similar colored objects from the background and kept the PixieCam trained to recognize the specific block colors daily, as well as adjusting the camera filters to keep any background detection to a minimum. The data display was written with PyQt and Python to neatly display all sensor data. This display included the distance output of the IR sensor as well as flag and edge detection alert system. The data display also included the color of the block and where the block was in the frame, represented by the 3x3 grid shown above. The arm sensors displayed the color of the block that dropped through the funnel and how far it is away from the arm.
This is a basic diagram of how the rover 2.5 worked internally. It would receive a message in this MQTT subscription task that would be subscribed to a topic that the rover sensors were publishing to. It would then interpret this message as an instruction. It would then send it off to the rover algorithm task, which would begin to move the motors via the motor movement task. But concurrently, this motor encoder task would also receive the instruction, and it would handle any error correcting. Once all of this has concluded and the instruction had concluded, we would publish to a topic using MQTT in this MQTT publish task. So the basic rover motor controls, we used a universal asynchronous receiver transmitter. So this was used to control each wheel individually. We transmitted the direction of the rotation of the wheel and the speed of the wheel. So basically, using UART, we can both receive and transmit, but we only cared about transmitting since we read encoder values in a separate task that I will talk about a little bit later. So these motor controls were dependent on the sensor readings. So if the sensor read that there was a block to the left, the rover would move to the right. If the sensor sensed that there was a block far away from the rover would move forward to get closer to it. So these wheels and these motors would be controlled using a PID algorithm. This PID algorithm, PID stands for proportional integral derivative. Basically, it would be using encoder values, and it would interpret these encoder values as distances. And since we were reading them at a specified time interval, we would also be interpreting these encoder values as speed. So basically, this algorithm was used to output the wheel speed. The input of this algorithm was the actual encoder values divided by the time intervals, which is the speed. The motor movement analysis was done using a serial peripheral interface. So the way SPI works is there is a master and slaves. The master in our case was the Texas Instrument Board, and the slaves were all 3-wheel encoders. So these encoders were read every 250 milliseconds. Considering the speed that the motor was moving and the distance, we wanted to read at a frequent pace. So we settled on 250 milliseconds. So these encoder ticks, we had to convert them to an actual distance. After testing, we landed on 1 millimeter is equivalent to 9.95 encoder ticks. So basically, we did all of our distance calculation using this encoder to distance conversion, which was partially difficult because of the inconsistency of the row of the encoders. Sometimes they would read more, sometimes they would read less. But this was a good middle point for conversion. So for the rover motor adaptation, we basically had a lot of translations to do in the rover. We had to be able to change human instruction into motor instructions. We had to be able to interpret the IR sensor and the Pixie Cam, which sent different types of information to motor instructions. So if an edge was detected, we would have to prioritize the infrared sensor and say, okay, we have to stop because we have reached an edge. And if we haven't reached an edge, but there's a block, we have to prioritize the Pixie Cam instruction. So this helped us for the orientation and positioning on the playing field. It also helped with the speed and angle movement of the rover, so whether we had to move faster or slower, turn 45 or 90 degrees, and it also helped for error correction, going back to the encoder values and being able to combine this PID algorithm and the sensor information for a more finely tuned movement. The rover and sensor integration. After an initial bumpy start, we were able to integrate them fairly smoothly. The infrared sensor was mounted 10 inches in front of the rover. As you can see in the picture, the Pixie Cam was oriented at a negative 40-degree angle, proportional to the horizon. So it was pointed at the very top of this unit collector, as you can see at the bottom picture. This was just to make sure that the Pixie Cam was only seeing blocks that we needed to collect, not blocks that we collected or items off the playing field. And this was the ideal positioning for the combination of the Pixie IR sensors and the actual rover motor control.
The purpose in our project for the 3DOF arm was to sort a colored block based upon its distance from the arm and its color into one of two bins. The arm specifications were as follows. It had 180 degrees of base rotation. It was able to move along 3 different axes. It had a reach of 12 to 21 centimeters and was able to reliably pick up a 1-gram block. Each of the servo motors used in the arm were 9-gram SG90 servo motors, accepting a PWM pulse of 1 to 2 milliseconds over a 20 millisecond PWM period. Applying a pulse of roughly 1 millisecond gave a rotation of negative 90 degrees. Applying a pulse of 1.5 milliseconds gave no rotation, so a 0-degree position. And applying a pulse of 2 milliseconds gave a 90-degree rotation. The arm had spots for 4 different servo motors. There was a servo motor in the base. There was one controlling the height of the arm, the reach of the arm, and a 4th one was controlling the opening and closing of the claw. Here's the arm control loop. It is broken down into 2 main sections. There's the motor control thread and the motor movement thread, and then the MQTT publish, MQTT subscribe, and MQTT read threads. The motor control and motor movement threads were part of the core control loop of the ARM, meaning that they were responsible for reading and executing messages in the form of the ARM's API. The motor control thread would send movement messages into a queue read by the motor movement thread, following the API set in place for the servos. And once the requested message has finished executing, an acknowledgement message was sent back through a motor control queue back to the motor control thread. The MQTT portion of the control loop was as follows. The motor control thread would send acknowledgements back. The motor control thread would send acknowledgement messages to an MQTT publish thread, which was then read, to an MQTT publish queue, which was then read by an MQTT publish thread. That MQTT publish thread was responsible for calling lower level functions in the MQTT code to publish to the MQTT broker. The MQTT broker was also read by an MQTT subscribe thread, and the MQTT subscribe thread was responsible for pushing de-JSONifying control messages from the PixieCam and pushing them into the MQTT subscriber thread, which was then read by the MQTT read thread. The MQTT read thread would follow the same API accepted by the motor movement thread and push messages following that API into the motor control queue, thus assimilating back into the two-state ARM control loop. The ARM was almost perfectly reliable. It ran for a very long time and was able to pick up blocks with almost full accuracy, given an accurate distance. Sometimes the PixieCam would not deliver an accurate distance, which resulted in the ARM either missing the block or not picking it up square. It was reasonably robust as well, although there were a few conditions that would break the robustness of the ARM. Three of those conditions were an incorrectly formatted JSON message, a color in the JSON message that was not red or green, or a distance in that JSON message that was not within the range of 11 to 21 centimeters.
For the final component of the project, we needed two objectives done. First, we needed color and distance information for blocks to be sent to the ARM over MQTT, and we needed to control the conveyor system. We decided to use the PixieCam 2 to detect block color and distance. The sensor was not optimal for distance detection, but we were able to get it accurate enough without the need for an additional sensor. As mentioned before, we decided to use ECE4534 to talk with the PixieCam because it was fast enough for our purposes without the expensive overhead. The design for this component was multi-threaded and made use of queues to talk between tasks. A timer callback was used to feed a start message into a queue that was read from by the sensor polling task. The raw data from this task was then sent in a queue where the color of the block was determined and the distance to the block was calculated via a lookup table based on the height of the block in pixels. This data was then sent via queue to the main task, which would stop the conveyor using a GPIO signal and send a message over MQTT to tell the ARM that a block is waiting to be picked up with the color and distance information to allow it to be sorted. This controller task would then wait for an act to be received from the ARM before turning the conveyor back on and continuing data collection. This component had a decreasing reliability over the semester. After running the I2C polling for extended periods of time, I2C bus faults became more and more frequent. Aside from this, the block color was always detected properly, and the distance detection was accurate to 1 centimeter about 95% of the time. The biggest fault in this system was the conveyor, which would drop about 1 out of every 4 blocks. This system was mostly robust though, excluding the growing number of bus faults and any foreign object falling in the way of the pickup zone, since we currently did not have a way to detect if this happened. Lastly, throughout this project, we have learned that communication between the separate components is the trickiest part. Making sure every team member knows exactly where their parts line up so as not to leave any holes in the design. We did figure out that integrating communication between the components is most easily done over a server, since the components don't have to be moved from one board to another, and the code itself does not have to take on any big changes. To increase the reliability for the rover, more IR sensors could be placed on the rover for edge detection, as well as refining the camera. Lastly, using an IR sensor instead of the PixieCam to detect distance to blocks would have made distance detection much easier and increased reliability.